Hi, everyone. My name is Lydia, and this is Foresight's Molecular Machines group. And today, we're really excited to welcome Dr. Ali Shaib. He is presenting from Germany. So please feel free to take it away.
Thank you. Thank you for having me. It's a good morning for our colleagues in California, and perhaps a good evening for our colleagues if we have colleagues from Germany and Europe. Thank you for having me today. It's a great pleasure to be here among you all, and I'd like to extend my gratitude for the Foresight Institute for hosting this event. Today, I'll share the story behind One Microscopy, an innovative technology that not only leverages accessible and inexpensive resources to achieve high resolution approaching 1 nanometer or better, but also enables the detailed description of protein shapes and perhaps structures using fluorescence light microscopy. So we'll embark on this journey for the next hour or so. And the disclaimer, I have a habit of running over time. So if I'm indeed like this, I'd like to ask the moderator to stop me at the 40 minutes limit. And of course, please feel free to interrupt me, ask questions during the talk. I'm happy to engage with you throughout. Let's start by a brief introduction about super resolution microscopy. So it has been 151 years since Ernst Abbe introduced the light diffraction limit theory, which states that the smallest distance that can be resolved between 2 points in an optical system is limited by the wavelengths of the light and the numerical aperture of the lens of that system. This sets the resolution limit of around 250 nanometer for visible light, right? And a staggering 119 years since Einstein's work laid the foundation for breaking the diffraction limit theory through his contributions to quantum mechanics and the explanation and understanding of the light nature as existing as both as particles and waves. His explanation of the photoelectric effect demonstrated that light can be existing as discrete packets of energy called photons, which is a significant departure from the classical wave theory of light. This dual nature of light, both as wave and as particle, was crucial for the works of Erwin Schrödinger on the Schrödinger equation, along with pioneers Werner Heisenberg on quantum mechanics and the Heisenberg uncertainty principle, and of course Max Born on the Born rule and the interpretation of quantum mechanics. All this work combined together was critical and crucial for the theoretical underpinning that have enabled the development of super resolution microscopy. And surprisingly, only 30 years ago, since this was actually contributed to breaking the long-standing diffraction limit theory that was first coined by Ernst Abbe. And this is, of course, we all know the work from Stefan Hell, which relied these principles in quantum mechanics to develop simulated emission depletion microscopy, that for short, in 1994, and the rest is history, of course. It allowed a beautiful resolution achieving 60 nanometers, and we all know what happened next. And since then, many other technologies that tried to push even this limit, from the Storm, DNA paint, MintFlux, Minstead, and our own technology, One Microscopy. In this talk, I will try to show you or convince you how we are actually approaching and bridging the gap between fluorescence microscopy and the ultimate best current imaging resolution we have, which is X-ray crystallography or cryo-EM. And that is not because we're better than the state-of-art super resolution technology. By far, we're not. It's because we utilize some aspects that were possible using expansion microscopy, and I will come to this point during my talk. What is One Microscopy? Just one moment, I need to clear something here and close my email because then notifications will start popping up. Okay, sorry for that. The One Microscopy relies basically on expansion microscopy, and expansion microscopy was first introduced by Edward Boyden at the MIT. It's inspired by gel polymers used in baby diapers, as seen in this nice image, where they basically saw that, okay, we can embed biological specimens into gel polymers, crack them into tiny pieces, and then we add water and expand them. Like diapers, when used, they basically swell. This also present, by the way, in the astronauts' suits. And the beautiful part that using epifluorescence microscopy and an physical expansion of the specimens with their original protocol, the X4, they could achieve 60 nanometer resolution, which is already at the level of STED microscopy. And 2 years later, they introduced an iterative expansion microscopy, allowing, after a very lengthy protocol, I must say, an expansion of 20 times. And this then brings the resolution down from using wide field epifluorescence microscope from 60 nanometers down to 25 nanometers. But the protocols were really difficult to employ and were very lengthy and involved multiple rounds of modulation and expansions. In 2018, Silvio Rizzoli, which I'm now in the current in his lab, they introduced the Extend protocol, and Extend protocol relied on complete chemistry. The beauty of this gel chemistry, the beauty of this protocol is that with one shot expansion, relatively very short protocol, you can achieve Extend. And then this brings down the resolution while using epifluorescence microscope 20 nanometers. We are in the realm now of palm pre-storm. And that means that now we're pushing this super resolution, make it available for any lab equipped with just simply an epifluorescence microscope. Of course, you need a decent camera for that. And later that year, it was the work of Helge Evers and the first author on, I believe, Meng-Fei Gao, where they combined first time expansion microscopy with super resolution imaging. And it was STED. And the Helge term, they gave it the term, coined the term Extend, and they reported, as we see here, a resolution down to 10 nanometers. This was actually pretty beautiful work, but one would wonder why it's 10. Let's just have this theoretical experiment in mind. Let's say that you have STED resolution. A decent STED is 60 nanometers. Of course, you can surpass this if you have better sample prepared, maybe 35, 40 nanometers, but let's say 60 nanometers resolution, and you expand your specimens 10 times. Then the theoretical resolution should be below 10 nanometers, should be 6 nanometers. But they could not really report that, and this is also to understand that STED in its nature is photon hungry. It requires a lot of light, and when you expand your samples 10 times, you're actually expanding it 1,000 times by volume. That means you dim the entirety of your sample and becomes so light deprived, where STED will work for densely labeled specimens. But if you have, let's say you're looking at big loot on the vesicle where you have only 4 copies of this protein, then the signal might struggle to apply STED imaging on it. Why it's 1,000 times by volume? Of course, because it's expansion in 10 times in the X direction, 10 times in the Y direction, and 10 times in the Z direction. So this is 1,000 times per voxel volume. But nevertheless, they could surpass the 20 nanometer resolution based on other protocols when they combined it with STED, and they showed very beautiful demonstration of tubular images in their work. In 2020, Jörg Spiekeldorf and Saad introduced a very easy iterative expansion microscopy, much easier than the original protocol by employing, and they showed very nice data at the resolutions approaching 20 nanometers or slightly better using simple fluorescence microscopes. And in the same month, in 2020, there was this beautiful work from our collaborator and friend, Markus Sauer. Of course, you're familiar, if you work with super resolution, you're familiar with him, that he invented the D-Store, where he combined expansion microscopy by single molecule localization microscopy, in this case, D-Storm. And the achieved report resolution was also 10 nanometers. Now we would wonder, how is that? Why it's only 10 nanometers? Because we all know a good storm is between 15 to 20 nanometers. And let's say you expand it 10 times, you should get 2 nanometers, at least 2 nanometers, if not better. So there's some notification showing from Zoom, but if you have questions, just please unmute yourself and go ahead and ask me. I would love to have them. I can't follow someone raising their hands also. Why they could not achieve lower than 10 better than 10 nanometer resolution? Because for storm to work, you're perhaps familiar that it needs blinking buffers for the fluorophores to blink, and then you have this storm effect. And blinking buffers have salts. Gels do not like salt, so you shrink back the gels. Let's say you started with X10, you end up something with X2.5, expansion factor of 2.5 the specimens, and hence why they ended up with 10 nanometer resolution. And then in 2020, later in that year, Ed Boden his lab introduces expansion labeling. And it's just a very nice protocol where also the concept of post-expansion labeling, and then they call it labeling because you achieve this very elegant concept of decrowding, where you expand your specimens and then you explore your probes, and then you come with the labeling probes. In 2022, again, York and Ångström introduced this very beautiful paper where they termed it pan-expansion microscopy, where they label everything with NHS ester. These concepts, of course, labeling protein densities with NHS ester was in the fluorescence field for 50 years, and also this concept introduced by Joshua Vaughan in FLAIR microscopy, but it was York's and also Amsad who first combined the NHS ester pan labeling with expansion microscopy. And they had this nice trick where they slip up the lookup table, and you get basically EM-like images. They combine it, of course, with antibody labeling, and where you can look like with EM-like images, black and white, some nice dots of pre and post-synaptic markers. Their work actually helped people realize that expansion microscopy is not too bad. You do preserve some information at the level of single nanometer digits. And it was in 2022 when Silvio and I introduced on bioRxiv the One Microscopy, which basically we surpassed for the first time using expansion microscopy, the 10 nanometer barrier down to 1 nanometer. And I will show you how basically. Before we do, let's go through the basic principle of One Microscopy. Basically, let's say that you want to see a single protein molecule. And the easiest would be to look at one of the primary or secondary antibodies that you have in your fridge for labeling. You bring this purified protein, you put chemical anchors on it, you polymerize it within a gel, you destroy this protein with enzyme or heat alkaline-based treatment with some autoclave, some pressure. You break it into tiny peptides that are still bound to the gel by the anchors. And then we use NHS ester labeling. How does this work? Of course, NHS ester chemistry will attack all the amine groups that are on your protein. In your protein, basically, the protein has an N and C termini. It will attack the amine group there, but also all the lysine residues. But that's not all, mind you, because now if you see this protein here in this cartoon, it's broken to pieces that are anchored to the gel. Now, every single piece of this is a peptide on itself. So you have the newly liberated amide group side group that you can also label. And that's basically how we can outline the protein shape. We put it inside a chamber to stabilize the gel, and we do rapid fluorescence imaging where these fluorophore fluctuate. And then we process that with the one plugin, which is based on Ricardo Henrique's protocol that was published in 2016. And a slightly modified version. And you can see here, this is your antibody image. There's no averaging here. We just acquired 2000 frames. We analyzed the fluctuation of this. And then we can see one snapshot, one image from one protein molecule using fluorescence microscopy. So of course, you can apply this imaging technology to image single molecules, as I showed in these cartoons. You can look at protein assemblies. I will come to that later in my talk. You can look at subcellular structures in 2D cell cultures, but also organelles in tissues. So then let's show you some applied images, some examples from cellular structures. And any super resolution methodology, when you introduce a new concept in super resolution microscopy, you have to image microtubules. I don't know why, but we just did what everyone did. And you can see this image. So here you're looking at single tubules in non-expanded specimens imaged by STED microscopy. This is an expansion of extend, confocal, nothing really striking over here. And this is how it looks like in extend. I must admit, this was carried now 3 years ago. We are better at it. We can slightly achieve better images using STED. And this is what happens when we expand it 3.5 times using one microscopy. You can start to see, actually, with a bit of imagination, a helical arrangement of the tubulin itself. And this is a nice cross-section of it. And when we do the full one power with expansion microscopy of 10 or more expansion, that means in 3 more resolution, you start seeing this helical arrangement in a nicer pattern, but the cross-section somehow was looking not nice. Actually, this sequence is for the storytelling. The real experiment that we did, we started with extend and then, why we don't see nice cross-sections? What's happening here? At the time, we didn't know that we are actually resolving the single fluorophores on your secondary antibodies that were actually being expanded. Because they are proteins, they are anchored, they also expand, and the fluorophores are being separated. And then said, what happens if we decrease the resolution by decreasing the expansion factor? Then see the classical cross-section of the microtubules shown here. Of course, when we put this on bioRxiv, people like these images because they were unprecedented in their beauty, and they were like immediately went viral before being even published. Can we have something more meaningful aside from classical boring microtubule analysis? So you see here this nice protein example was theorized for quite some time now. It has microdomains or nanocolumns, PSC95. We asked ourselves, can we see these nanocolumns with our resolution? And let's see that we magnify this confocal image of a single postsynaptic density, and this is how we see it with one microscopy. To our surprise, it's not even nanocolumns, we call it nanodomains that are quasi-regular pattern. We like to give it the name of reticulum. It means like a grid or a net. This is just different views to label together with Homer 1, Cheng 2, another postsynaptic proteins that you see how they look like. Okay, and I must say that this is actually not possible just to see it with extent, because as I said, that the stent requires a lot of photons to see it. You see something that is resembling these nanodomains or microdomains, but we don't see this nicely described quasi-regular pattern of the PSC95 using one microscopy. And if you do one microscopy with an epifluorescence microscope with a simple camera, not a confocal laser scanning microscopy, you don't really resolve the structure. So you really need to combine to use one microscopy and to use a laser scanning confocal system to see it. So next, then we asked ourselves how our work really compares to others. And to our surprise, that was very rewarding and pleasant for us. When we put this observation on bioarchives, a year and a half later, our colleagues in Heidelberg, Elisa Deste group, they use minflux, not expansion even. Another of course, state-of-the-art super resolution microscopy, and they actually reported the same arrangement of PSC95. So that was like really worrying. So we're not crazy. We're not imagining things or imaging artifacts over here. This arrangement of these nanodomains, we had the number of 6.788 nanometers. They have 7.08 nanometers. I think I trust here more minflux and that we had something wrong with the expansion factor, but this was very rewarding and assuring for us. This is also how our cross-section of a microtubule compares to minflux. So we're not really worlds apart. So that also we get it right on the minflux. Of course, we reproduced their work. And I found on bioRxiv, now it's actually published. Please, I apologize for the wrong reference. It's now published. But back in the day, I saw on bioRxiv this nice work from Stefan Saal and Stefan Hell on minflux, where they say, okay, we can also see two fluorophores on one nanobody that are about 3.7 nanometers apart. And I said, okay, can we reproduce that? I want to just copy their experiment the same. We expanded these nanobodies fluorophore, use similar cartoons, and this is their plot, and this is our plot. We found basically, yes, with using microscopy, simple confocal microscope combined with expansion microscopy and fluctuation analysis, we can get similar results to minflux. So this, now that our data compares to a good extent to the state-of-the-art super resolution microscopy, can we see protein shapes? And just as a reminder of the concept, let's say that you have a secondary antibody, you expand it, you break it, you label it, and then you image it. Our idea is that let's leverage what expansion microscopy have, where it does have an advantage over classical super resolution imaging microscopy, where you don't expand the specimen. Because let's say that you have a small protein like calmodulin, it's 10 nanometer or 9 nanometer on its longest axis. How many fluorophores you can fit on it in the classical non-expanded specimens? The fluorophore size is about 1 nanometer.
At best, if you have direct chemistry, no linkage error, no probes like antibody or nanobody or minibodies, you can put maybe 4 or 5 fluorophores. Then you see maybe like dots, right? But with expansion, since you are blowing up the structure in volume, and then you come with your probes afterwards, then you have the label, the dye size itself is inversely proportional to your expansion factor. So if you're expanding it by 13 times, then the probe is under 1 angstrom, the linkage error of the dye itself. And this is how we basically can outline the shape of the protein, like in electron microscopy, but we're not measuring electrons, we're measuring photons in this case. And then I will show you some examples. You're looking here at the secondary antibody adenovirus STAR635B. This is the antibody labeled as NHS ester. This is the fluorophores on the antibody here. Here, a human IgA example where you have two Y-shaped antibody on both sides. Of course, this we know from X-ray and cryo-EM that these antibodies are super flexible. Actually, this is how the antigenicity works, that they need to be flexible to find the epitope bend and so on. So it's not really surprising for us that they do look slightly different. And this is a human IgM with a bit of imagination. You can see the snowflake shape as reported in this cartoon, but more importantly, see the 5 different arms of the antibodies on this complex. Then we looked at autophagy, a protein essential for hearing. And this protein, for the time being, there's no X-ray or cryo-EM structure because it has a lot of disorganized domains between the subunits, and then it's difficult to crystallize except with this domain that there's a crystal structure for it. And when you try to do it in cryo-EM, because it has multiple different conformations and shapes, they simply average out. So there's no real structure of it. This is an AlphaFold prediction. And our one image is not really worlds apart from what AlphaFold predicted. This is another example of autophagy where this would be one image that's not cropped. And of course, here with some human bias, I cherry-picked those images that look like AlphaFold and I magnified them here. Of course, here's some bias. This is like a disclaimer here. But this is the entirety of one image that is not cropped. And the next, we look at a very small protein, calmodulin. As I mentioned earlier, calmodulin, upon binding its natural target for calcium atoms, undergoes a small conformational change. It elongates along its longest axis. And we could see that basically using one microscopy. So this small dynamic change, we could report it. These, of course, double-blind experiments. One scientist did the experiment, another scientist blindly analyzed them. This is just a gallery of hand-picked with some bias or a lot of bias calmodulin images. This next, I will show you images of our favorite protein. It's the GABA receptor. It's my favorite protein for a reason, because the preps that we get from Cambridge, our collaborator at Arishesco, are super pure, with 95% purity or higher, because this technology so far that I'm showing you, you label everything basically. And if you have contamination in your samples, then you wouldn't know what protein is what, right? And this is one uncropped image. I magnified with some bias images that resemble a GABA receptor. And I must say here that I think I'm running a bit late, 11 minutes. I must say here that the very first images that I obtained were a little bit frustrating for me, because the GABA receptor was looking longer than the X-ray structure that was solved by our collaborator, Radu Arishescu. And we repeated this experiment and wasn't satisfied. What is happening here? Why this structure is so long? And then when I showed this to Radu, he was like really surprised and very happy. This tiny part that you see here is the part that we could not crystallize, and you cannot see it in the cryo-EM because it's so disorganized, it averages out. And this is here, what we said, these loops here basically are hand and heart drawn. So these are single snapshots where we could really see it in one microscopy, while X-ray or cryo could not really solve it. Here are hand-picked GABA receptor images, single molecules in different conformations. We wanted to do one experiment to look at our expansion factor, how good it is. We got one prep from Radu. He did the 2D classes of cryo-EM structures. And this GABA receptor now have 5 nanobodies that recognize each of the 5 subunits on this protein. Each nanobody have 2 fluorophore in different color. And we labeled NHS ester chemistry, the receptor itself. You see here the 5 nanobodies. Here, the first nanobody is 2 dots. The second, third, fourth, the Fifth could be that this nanobody inverted inwards, or it's simply that one of the fluorophores were missing. But the most beautiful, rewarding part for us, that indeed the expansion factor would match the ground truth structure.
May I ask
So
a
that-
question?
Please go ahead.
So these cryomicroscopy pictures are very detailed, arguably more so than the one microscopy pictures. So what is the advantage of the one microscopy over cryo-electron microscopy?
This is an excellent question, and thank you for pointing this out. By no means, one microscopy has better resolution than cryo-EM. Cryo-EM would be the ground truth here, and the resolution basically is atomic, or subatomic in Ångström, right? So but we do have some advantages over classical cryo-EM. First of all, the first prep that we received from Cambridge were on a Thursday afternoon. The first one images that I showed you were on Sunday morning, so that you can achieve snapshots without any need of averaging. This is one molecule, one image of one molecule. You don't need to get hundreds and hundreds of thousands, remove 2/3 or 4th or like 70% of these images, and take a lot of time to reconstruct a good model. So this would be something intermediate, something that helps you. Do you want to see some changes, some conformational changes, or some indication? Is it worth to do cryo-EM or not? So the one microscope could help you here. Another advantage is that you can look at protein complexes in multiple colors. Here, for instance, cryo-EM will be black and white, imaging electrons. Now we can look at the receptor itself and the nanobody, the fluorophores on the nanobody. And one can be creative. You can do it multiple color at a resolution approaching 1 nanometers. But indeed, you're absolutely right on spot. Cryo-EM will always be the ground reference in this case. And we will compare our work with it. It's just like complementary work, could be as complementary or intermediate step. And it could show you something that, as I mentioned earlier, X-ray or cryo-EM could not show because of being disorganized, and you can't really simply average them. I hope this answered your question. Then we asked ourselves, can we go better? We did simple 2D averaging. It's not the best image, but it did go better. But all of this, there was some cherry picking here, and there's some human bias into all this analysis that I showed you. Can we do some sort of analysis where there is little to no human bias? And the answer is yes. So we can do more using the magic word. It's very trending these days, artificial intelligence. So how does that work? We detected and segmented one images into individual protein molecules. In this case, it was GFP, labeled very boring, compact, barrel-like structure. Then we use an existing, very beautiful concept from Ellen Zhou. By the way, she also worked for a brief moment with Ed Boyden before this work. And they posted on archives the CryoFire, which is a modified version of CryoDragon, a published version of CryoDragon, where they do not need to assume the angle and the positioning of the molecules for 3D reconstruction. And this solution was ideal for us for a reason, because our proteins are floating in the gels. They are like monolayers, but they are in different orientations, and we don't know the angles. We have a maximum intensity projection of this protein as it was in the gel. So this is our solution. Of course, we have back in the day, now we're improving and working on our own solutions. But back in the day, there was this very talented bachelor student for his bachelor thesis. He adapted this, and we modified it in a way that it would work for fluorescence microscopy, because this is for electron microscopy images. They were imaging electrons. So that we introduced some parameters where we extracted density points and some hyperparameters where we added, I will not really go into super details into this, but we can discuss if you're more interested into it. We could correct for expansion factor, we feed it into the decoder, we do some translation into the Hartree Fourier space, then 3D network, then the 3D reconstruction. These are the first images where we tested this neural network for a sanity check. Very, very simple, boring thing. So like after 2 fluorophores normally, can we get 2 blobs? And indeed, we could get them at the distances that you would expect from this ground truth cartoon based on X-ray data. And this is not updated, sorry, of course this is published. And then how does this compare to X-ray? Back to your question. Of course, we do not compare. This is X-ray is way, way better. This resolution here is not cryo-EM. I apologize for this mistake. This is an X-ray structure. It's 0.2 angstroms here. Our resolution was from 900 or so, 900 GFE molecules imaged around from 20 images, 1.5 hours in one afternoon, generated around, if my memory is not failing me, around 18 angstroms resolution. But the rewarding part for us, of course, this is here, sub-angstrom resolution. Here is to the right, our image is 18 angstrom. The rewarding part was two things. The first, we do see a barrel. We didn't get a bead ball. And the expansion factor is comparable to background tools. That means we're doing this correction and computation to a certain degree correctly. So this was quite rewarding for us. Then say, can we do something more complex? Can we look at the GABA receptor? Yes. On the far left, you're looking at the 2D1 images. Then you have your X-ray crystallography with this axis that we know there's some missing part. Oh, I apologize for that. Some missing part here. This is the AlphaFold prediction. It can predict it in an open or closed conformation. Of course, it's also missing all the other disorganized parts. This is really one image reconstructed from about 4,938 molecules. You can see that the 5-fold symmetry, of course, is not as beautiful as the ground truth X-ray. But the nice part that we could see what the X-ray crystallography could not really determine. And this is when we imposed 5-fold symmetry, like what they would do in cryo-EM, based on the advice from our cryo-EM expert, Eduardo Arishescu, our collaborator, of course, a leading figure in the field. And we could see actually it's not, of course, the X-ray is much better, but from 4,000 images, 2 weeks of imaging, we're starting to get what you would resemble a GABA receptor using fluorescence confocal microscopy. Yes, when you get bored of me, guys, just interrupt me. So can we see smaller things? Can we see peptides? I showed you images of proteins. Can we see peptides? Yes. So we looked at an M-Link, a molecule that our director introduced like 15 years ago. It is a membrane label. Why we chose this? Because it has several lysine residues. It's nicely anchored into the joint. It has a blinking auto dye here. We anchored it, we expanded, and you can see this is NHS ester labeling the lysines, and this is the fluorophore on the top of the dyes. And of course, we did this in unicolor because of chromatic aberration concerns, but we also did it in two colors, and we could image 1 nanometer or lower than 1 nanometer distances in both configurations. Can we reproduce this? The answer is yes. Of course, these are all slides. A year and a half ago now, we are collaborating and working with many other labs than what I showed you here. But since we're putting it on YouTube, the other work is not published. So that's why I stick to what we publish. We could reproduce the GABA receptor and the nanobodies under industrial settings from Leica. We could reproduce it in our collaborators lab in Hamburg, SR, the GABA receptor here, you can see it. We could reproduce it in Markus Sauer lab in Würzburg. You're looking at tubular structures. We could also reproduce it at the MIT United States in tubulant. Here, the tubulins looks very beautiful, actually, because they expanded them X20. They also could reproduce it at the MIT using stick tissue sections where they labeled bassoon, an active zone synaptic protein. You can see the super resolved images that there actually is some sort of arrangement of this protein. These are individual vesicles, by the way. So yes, it can be reproduced. You can also do it starting from multiple microscopes. You can do it here as shown here in the pre and post synaptic structures using epifluorescence microscope. Of course, it will not give the highest resolution, but still pretty decent. You can use an older Zeiss microscopes, newer Zeiss microscopes, Iberia, relatively old. Most of the data that I showed you, by the way, is on a microscope purchased by Silvio in 2007, SP5, like a confocal microscope, pretty old. You can also do it on newer microscopes like the Stellaris 8. Can we do something useful? Basically, what I showed you, you could see in the single protein molecules, you would see it better actually in X-ray or cryo-EM, and some of the other data you can, if you're rich lab, you have super resolution microscopes, you can generate this. Can we do something like actually meaningful? It's tricky to do it with other technology. The answer is yes. We have in our freezer a lot of CSF, cerebrospinal fluid, from Parkinson's patients and neurological samples. and I will try to finish in the next 2 to 3 minutes. And we labeled them against alpha-synuclein nanobody, and we expanded them, and we could actually see the different assemblies that are described in the Parkinson's field and the alpha-synuclein world. You can see the single copy here, the large assembly, the very large assemblies, and the smaller assemblies that are hypothesized to be the toxic monomers. The beauty of this work that do you see here the cryo-EM ground truth structures of this? The beauty in what we're showing, what I'm showing you here, is that these are directly imaged from patient samples. They are not overexpressed in artificial systems. One time you overextract them and then you can reconstruct the 3D structure by cryo-EM. So this is like directly from the specimens from human patients. I will skip this slide technicality that you need smaller linkage error to see the shapes. If you use antibodies, you will not see it, but I'm running out of time. I warned you, I speak a lot, sorry for that. But the beauty of this experiment is that we do see the large and very large assemblies that are hypothesized that are not toxic equally between this red Parkinson's disease patient and the neurological control patient without Parkinson's disease, while all the smaller toxic assemblies are higher in patients. And this is just some statistics where we show that if the alpha oligomer synuclein score is 1 or higher, that the patient is at higher risk. So as a conclusion, I showed you today that through one microscopy, it is applicable to cell culture tissues, single molecule specimens. I also showed that one reaches a nominal resolution of 1 nanometer or better in the case of M-Clink. I showed you that the 2D images can be reconstructed in 3D volumes. And this is some shameless advertisements. I'm on X, on LinkedIn. I tweet food, cats, sometimes science. And we also have some nice tool. If you do fluorescence imaging and you measure exocytosis or calcium waste or what have you, we have this tool for you, ID on bioarchives. It's basically download, plug and play. And we are next year, in January, it's the 10th anniversary of expansion microscopy. Silvio and I are celebrating this event by having all the major names in the field, of course, together with Boyd and Marcus and all the big XM players, but also super resolution scientists and biotechnology companies to celebrate this event. We will stream this online as well. And with that, I would like to thank the director of our institute and the head of our department, Silvio Risoli. Without him, the work would not be possible. My group, our Risoli Lab collaborators, our external collaborators, and of course, this lovely audience. I speak out, I apologize for that. I take any possible questions from you.
I think Kriyan and Steve had some questions in the chat. Maybe Kriyan, would you like to go first?
Yeah, this is all lovely stuff and super cool. And I just wanted to say what I said in the chat, which is that quantum mechanics does not allow you to beat the diffraction limit. Instead, it is diffraction patterns combined with fluorophores. And if you can assume that the fluorophores emit point sources, you can localize them to within sub-wavelength. But that's not beating the diffraction limit. That's using prior knowledge about the emission and using the diffraction patterns. Yeah. And then the other thing is, I wouldn't say that expansion microscopy allows you to beat the diffraction limit any more than stretching something out would allow you to you make it bigger. And so you claim 10 nanometers resolution, but it's not actually 10 nanometers in what you're imaging. It's 10 nanometers in the thing as it was before you expanded it. But nonetheless, this is all great stuff and super useful. So this is technical. And the last thing I'll say that's technical is that actually you can derive the diffraction limit from quantum theories, 2-line derivation using the uncertainty principle and the de Broglie relationship, and you get the
So I agree to these technicalities. Thank you for pointing this out. But then how would you describe resolution? What is resolution?
That's a big topic. Resolution, it's strange, but it relates, among other things, I don't mean to make it too crazy here, like it relates to the information that is conveyed to a human.
Exactly. If you can see it, that means you can resolve it. Do you agree to exactly? So this is what this is in this context. This is what we call resolution. But if you're with the technicalities and the absolute definitions, you're absolutely on spot. But you say if you see it, you resolve it. This is your resolution. This is what we're saying here.
Oh, I have one more question, actually, then I'll yield. So I asked you about the advantages of one microscopy versus cryo-electron, but isn't another advantage that with your techniques, you can label different target molecules and that you cannot do with cryo-electron?
Absolutely. You have it in colors. One electron microscopy is unicolor. Exactly. This is one of the major advantages. This is actually what we're doing currently.
Okay, I'm done.
Thank you. Thank you.
This was my first introduction to expansion microscopy, so thank you very much for an excellent presentation.
Thank you.
One of the things that I've noted recently is that many of these biological systems are so complicated that it's very difficult for anybody to comprehensively study and integrate them, which is leading towards AI-assisted learning and modeling systems. And I'm wondering, to what extent could you feed different sequences of structure? So as I commented in my question in the chat, beta tubulin and alpha tubulin bond is broken by mercury. And so you could do an expansion of just using mercury, or you could use a series of proteases to break down some bonding and create different peptides that are being expanded. And even disulfide bonds can be broken by reducing thiols. And if all of these were done in parallel and fed into an AI system, how much more information could we learn?
I don't know if you noticed, but I was taking notes because these are brilliant ideas. I don't have an answer to that, but it's definitely doable. And I don't have the big AI team. Of course, with Sylvia's help, is helping me grow an AI team. We are now by we, I'm the editor in the group because I don't know anything about AI except from what Copilot tells me. But the team of 4. And we're working on basically on either the 3D reconstruction, but also detection and segmentation, and also enhancing the fluctuation analysis, not just using fixed mathematical formulas over there. But this is brilliant. And you're saying basically, if I understood you correctly, and I think we should test that, is that can we change the quality of one images that we get by simply changing the peptide interaction by either breaking the alpha beta tubules or the disulfide bonds, and then can we basically teach the AI or the neural network, and then when we feed it another images of different proteins, can we tell what is what? Is this what you're saying, basically, right?
Yeah.
So
to refine the resolution based on different sequences of subunit in the disassembly process. So if you take the alpha beta bond apart and then you digest it with a protease, you may get a different pattern than if you do it in the other order.
This is fantastic, and I'm happy actually to follow with you one-on-one with by email. This, I think, something we should definitely look at. And interesting.
Thank you.
Sure.
Does anyone else have any questions? Okay. Thank you so much, Dr. Ali, for joining us. And
thank you for having me.
yeah, if anyone thinks of anything or would like to connect, feel free to do so over email. So
absolutely. I might reach out for you, Stephen, just to follow up on these ideas. It's very interesting.